We're in a 2014 JK Wrangler with a LT 6.2 L86 engine. The L86 engine has got a lot of technology in it. It's direct injected, continuous variable valve timing, tremendous torque on the bottom end. Merging onto the freeway here is like, that's barely touching the throttle. We're at freeway speed. Do you need an L86 in your JK? Probably not. Do you want one in your JK? Probably. This engine has so much torque. It's like a diesel. It'll move this heavy JK with 40s up this parkway like nothing. It'll tow 8,000 pounds. And with all the technology they have built into this engine, this is an 8-speed automatic transmission, continuous variable valve timing, direct fuel injection, enhanced airfield management. We'll talk about those because I think we pretty much talked about everything else on these Gen 5 8-speed swaps. Direct injection allows you to run higher compression on lower grade fuels. It puts the fuel directly into the combustion chamber rather than behind the intake valve. It requires high pressure, thousands of pounds of fuel pressure, to get that fuel injected into the chamber directly. And GM has done it on the Gen 5 engines. There are some downsides to direct injection. European cars have been running them for a long time. Blow-by and carbon buildup. There is no fuel on the back side of the valve to clean it. GM has some patented technologies with valve timing to keep the carbon buildup from happening. And I can say the few Gen 5 engines we have torn down have proven to be extremely clean. There is a little bit of blow-by on any of these direct injected motors if you choose to put a catch can in. The LT1 does run a catch can setup. The truck motors do not. In my personal Jeep, I wouldn't be too concerned about it, but if you're one of those guys that is very particular, you might want to put a catch can in. Other than that, the Gen 5 motors are very low maintenance. They do run on a lighter weight oil, 020, full synthetic. Continuous variable valve timing is big. Variable valve timing can help you control cylinder pressure. In the old days, if we wanted to get more power, we'd put a bigger cam in. Putting a bigger cam in would yield more power by getting more area under the curve, more fuel and air mixture into the chamber, especially at higher RPMs. The problem with that is most of the bigger cams would increase the valve timing duration. So on the intake cam especially, or the intake valve, you would leave it open longer. And if you leave the intake valve open past bottom dead center, the piston starts coming back up, and then you end up blowing that charge back into the intake manifold. What that does is it lowers the intake manifold vacuum and dilutes the mixture in the intake manifold, so you end up getting that rump, rump, rump. What variable valve timing allows you to do is essentially have two cam profiles by retarding and advancing the camshaft. So at low RPM, you can advance the cam for more cylinder pressure on the bottom, and then at the higher RPM, you can retard it to get that later valve timing. What continuous variable valve timing does is it allows you to control the camshaft anywhere between the park position and the full open position. With discrete variable valve timing like the Gen 4 motors had, you basically had two positions, parked and open. So you would be in the advanced position off the line up to about 3,000 or 4,000 RPM, then the cam would phase to the retarded position and you'd get another burst of power. With continuous variable valve timing, we can control that cam at any point we want. So if you give it some throttle in the mid-range, instead of the transmission downshifting, the computer may just decide to phase the cam, and that'll give you that extra torque, that extra cylinder pressure. Now all this is tied in with the fuel you're running, and these engines can run the lower grade fuels with a direct injection to prevent carbon buildup and NOx emissions, or nitrites of oxygen. NOx emissions are a problem when you build up too much cylinder pressure. So the manufacturer has to set up the valve timing very carefully. Building cylinder pressure up is great, but there's also rules as far as emissions goes as to what they can do with it. So GM really had to put a lot of technology not only into the hardware but into the software and the calibrations to make these direct injections work properly and get the maximum efficiency. I heard that they did experiment with a cam in a cam on the LT engines so they could phase the intake and the exhaust independently like a lot of the overhead cam engines, but they determined that the gain was just too small for the complexity and the overall length of the motor was increased, so they dropped that. And personally, I think they did an excellent job on this motor. It really is unbelievable how much bottom end torque these things have. I'm driving what is probably a 6,000 or 7,000 pound JK with 40s, and just touching the throttle, this thing goes like a go-kart. This motor is limited on the top end, having enhanced airfield management, and let's talk about airfield management. Airfield management is essentially turning your 8-cylinder into a 4-cylinder, almost. This technology has been around for a while. A lot of you probably remember the old 864 Cadillacs, which weren't very successful because back in the 1980s, cylinder deactivation was not a very well implemented technology. Basically what they did is they shut lifters off, but they were using carburetors, and when you shut 4 cylinders off, you need to compensate with a throttle body, and the earlier Cadillacs couldn't do that. So they were very limited on their success. Since the Gen 4 LS engine, airfield management has become widespread. And not only with General Motors, but Chrysler has MDS, multiple displacement, Mercedes, Honda, they all have this technology now. And essentially what you're doing is reducing what's called pumping losses. Pumping losses are when you're at less than wide open throttle. And what that means is an internal combustion engine is most efficient when you're at wide open throttle and you have no intake or exhaust restrictions. But as you know, we have to throttle these engines so we can drive them around. When you're at part throttle or idle, the pistons, when they are moving down, is fighting vacuum. The valves are closed, and there's a lot of energy involved here. It has to overcome that vacuum to pull the piston down, and that's just lost energy. Then when it goes back up, the valves open, you blow out the exhaust. Really what it is a pumping loss fighting that vacuum because of the closed throttle. What airfield management does is it essentially disables those cylinders so they become air springs. And what I mean by that is the piston does go down and it does suffer that pumping loss. But when it goes back up, the valves remain closed, so it builds up pressure. And then on the next stroke, the pressure built up pushes the piston back down. So it's an air spring pushing that piston back down, which means it doesn't have to go back down and suffer those pumping losses as if the valves were functioning. There is a gain in airfield management because you can take the displacement of a larger engine, let's take this 6.2, and cut it in half to say a 3.1. And we all know that the smaller engines have better efficiency. The smaller engines are trying to mimic larger engines through forced induction like superchargers and turbochargers, and the larger engines are trying to mimic smaller engines through technology like airfield management or MDS. And it does work in a light JK, in my experience. It doesn't work very well under a heavy load, and there's reasons for that. When you're under a heavy load, you want as much torque as you can get. That means the larger displacement engine is going to be more efficient. When you're under a light load, turning into a 4-cylinder can help and actually get you a few % better mileage. And I don't think it's very dramatic. It's nothing like double digit. Maybe if you could stay in the 4-cylinder mode all the time and drive the throttle so that it doesn't kick into the V8 mode, you might get 10%, but my experience is more like 2 to 4% better mileage in a light JK. If you let off the gas and you're coasting to a stop, you go into what's called deceleration fuel cutoff. So you're not using any fuel at that point, and airfield management doesn't help you at all. Where airfield management is going to help you is when you're under a light cruise, and that's pretty often in a light vehicle like a car with small tires, or even a JK with small tires. The Gen 5 motors have enhanced airfield management. They've used technologies that allow the engine to stay in the 4-cylinder mode longer. The direct injection and the high compression, the continuous variable valve timing mean higher cylinder pressure. Higher cylinder pressure means that in a 4-cylinder mode we can put more torque out. We can stay in 4-cylinder mode longer than if we did not have those technologies. In fact, on these Gen 5 truck engines, they are in 4-cylinder mode quite a bit, So they've eliminated an intake manifold vacuum port. That means your brakes are not being powered by intake manifold or engine manifold vacuum. Your brakes are being powered by an external vacuum pump. These engines have an external vacuum pump which will supply proper vacuum even at an idle. And this is a big advantage if you go crawling. You don't need hydraulic brakes. This vacuum pump will put out plenty of vacuum at idle, so you have brakes even if you're at very low RPM and you're loading the motor down.